Okay, good afternoon. Welcome to our course in Cyber Physical Systems. Today we're going to start Chapter 6 that deals with systems engineering and software engineering. So we're going to start discussing an introduction to the overall discipline of systems engineering. And of course, we're not going to cover that in one section or two or three. In fact, we're not going to cover it in this chapter, but we're just going to give you an overview of it so we can create linkage forward to maybe a more expansive introduction to software engineering. And then take those two together and correlate it to the effects and the benefits that it can have for the working in cyber physical systems. So the chapter starts with an introduction to systems engineering so you know what we're talking about. And we're going to go through several formal definitions from some influencers and standards. And I have to tell you that I really like the discipline of systems engineering. I eat that stuff up, and all those definitions to me is like poetry. So we're going to go through that, and then we're going to discuss what are the challenges of cyber physical systems representation that taking steps in the discipline and the rigor of systems engineering can help us solve. That is going to lead us into a discussion in software engineering and how we capture requirements for software in cyber physical systems, which is a big part of not only software engineering, but systems engineering as well. So we have alluded to systems engineering throughout the course, and we also have mentioned that we're dealing with complex systems. So a response to deal with the complexity of systems is to follow a set of thought processes, methodologies, discipline. So since many years now, this has been embodied in a body of knowledge, which we call systems engineering. And the idea is to target the design, complex design, and integrate all the disciplines that are necessary to bring a design to life. Because if we're talking about a complex system, a good premise to have is that we're not just going to do it with a single discipline. So we have to be cognizant of the cooperation and the interdisciplinary nature of the systems. And cyber physical systems is one of these types of complex systems. So we'll see that at a minimum, you're going to see that any complex system is going to draw from the bodies of knowledge of control engineering, which it doesn't really happen in the United States as control engineering as a separate engineering discipline, but you should know that, for example, chemical engineering has a great deal of control engineering because, as I mentioned, one of the origins of control engineering is on chemical plant control. So they have that. And of course, electrical and computer engineering, they do touch on control engineering a great deal. So we're going to see also electrical engineering, software engineering, computer engineering too there, and some aspects of project management, which starts transitioning into the business aspect. What we're going to see is that systems engineering does not operate on a vacuum. It tries to look at the product and the project not only from a purely technical perspective, but also from a business and execution perspective as well. So all this, at a minimum, we have all this handful of disciplines, and it can go beyond that. So here are some definitions of systems engineering from some standards and also some influencers. And as we go through them, I want you to think about what are the common threads through all these different definitions. Some are longer than others, so some are succinct, some are not so succinct for a definition, but I want you to think about the common threads throughout them. So we have one here that says that systems engineering is the management function which controls the total system development effort for the purpose of achieving an optimal balance of all systems elements. It is a process which transforms an operational need into a description of system parameters and integrate those parameters to optimize the overall system effectiveness. So here we start seeing some specific things that I would like to highlight. So the management function. So a little vague in this definition. It's not really a management as you would think in the strict sense. It's really the management of the processes and the requirements, most importantly, the requirements. Because, and I can tell you from first-hand experience that I've seen projects go the wrong way because there is not a clear vision of requirements at the onset. And you can pivot easily when you have simple projects, but when you have complex projects, pivoting is very, very expensive. And as you go down the hierarchy, and further down the line of development, each step, that cost of pivoting is actually amplified as a rule of thumb by 10. So if pivoting at the system level, when you are doing your due diligence and considering things at the system level, if pivoting there costs a normalized quantity of 1, once you go down the subsystem and you have to pivot there and go back and retrofit and see what it means at the system level, it's going to cost 10x, whatever it is at the system level. And if you keep going down, it's going to cost 100x because you have to go up 2 levels. So you want to do all the strategizing and get a clear vision of what you are going to do, the requirements at the onset, at the system level, and start there. That is a big part of the philosophy of systems engineering. So we start seeing the management of the requirements, and it's also talking about the optimum balance. So it's not just to optimize one thing, but also look at the overall system holistically and see what is the overall optimum product or project according to some parameters that have been established. That is not a trivial problem because it's highly nonlinear and highly multidimensional. So it requires heuristics, modeling, different techniques, really a fusion of all those. So we have the next one, an interdisciplinary collaborative approach to derive, evolve, and verify a life cycle balance solution which satisfies customer expectations and meets public acceptance. That's an IEEE standard on systems engineering and what it is that dates back to 1994. That's, in the big scheme of things, that's not long ago. So here we see something new, the life cycle. So not only we want to optimize the product overall, the different dimensions, but now we want to optimize and have a balance across the life cycle. So systems engineering defines the life cycle into a handful of big chunks. The first one is the system design. The next one is the actual development. Then the next one is the manufacturing, or bringing to life whatever it is that you design, deployment, and then disposal. So those are 5 big chunks. And the way that we try, and it comes to us naturally to think about engineering, is that after that design is done, then we're done. But there is a whole aftermath of being able to manufacture something, of being able to deploy something that implies that you have to think about training, usability, maintainability, and then for some things, you have to think about disposal. Sometimes you want to force a disposal of a product because you want to introduce a new one. That's more a commercial, but there are many products where disposal is taken very seriously, right? Like weapons ordnance, for example. A big part of the design of weapons ordnance is how are you going to dispose of this? And the people that are involved think about that very seriously and carefully, because we do hope that we end up disposing of it. We do hope that we don't have to use them. So disposal is a big part of that life cycle. So that's introduced here. It introduces the word customer. Very important. And we're going to see also later on a different word, stakeholders or constituents. But it mentions customers. The customer many times does not understand what they need to do. A big part of systems engineering is elicit what the customer wants in a way that is sort of lay people terminology, and translate that into rigorous technical requirements. That's a big part of systems engineering. And also sifting through what is a wish, what is a nice to have, what is a want, and what is a need. Because everything costs something in terms of resources, of the cost of building something. So nothing is for free. So trying to really get to the bottom of what really is necessary to achieve and meet the customer's expectations is an important part. And then the other part of this, because this is one of the nicest, it has a lot there and it's very concise, the IEEE standard definition. The other one is that it meets public acceptance. So that talks about another set of care about where it's just not you as the developer doing your job and getting paid for it, and the customer getting what they want and reselling it and marketing it and making money. There is also an ethical responsibility part of it, that there is a public acceptance. If people knew what you were doing, would you be okay with that? Would you not be ashamed of it or embarrassed about that? So that part is important as well. All right, and another one, this is a long one. An interdisciplinary approach encompassing the entire technical effort to evolve and verify an integrated and lifecycle balanced set of system, people, product, and process solutions that satisfy customer needs. Systems engineering encompasses the technical efforts related to the development, manufacturing, verification, deployment, operations, support, disposal, and user training for system, products, and processes. The definition and management of the system configuration, the translation of the system definition into work breakdown structures, and development of information for management decision making. So that one, you can see a clear expansion beyond the one of the IEEE, but it has a lot there. So I'll try to highlight, other than the enumeration of all the things that are involved, such as people, product, processes. So complex systems is just not a physical entity. It may involve people as part of the system and processes in conjunction with some device or product that make up the overall system. It also mentions, and I did mention before manufacturing, but a new one here is verification. Verification, and we're going to later on talk about the differences between verification and validation. We're going to come back to this, but it's appropriate to mention so you can see and kind of get in the right mindset about the distinction, which is not subtle, really. So verification means that if I give you a spec and you design something to that spec, we verify against the spec, and if you did what the spec says, we have verified that your design is good. But are we done? No. Because how do we know if my spec was correct? Maybe my spec was totally wrong. And even though you follow the spec and comply with it, we don't have something that works. The next step is validation. Validation is matching to what the customer really wants and deploying that in the field and seeing if what was designed according to the spec works. That's the ultimate test. And that's why it's so important to be able to capture good requirements. Because if we don't capture good requirements, I'm pretty sure that engineers do a good job and can match a spec, but if the spec is not good to begin with, we don't have a viable system. So that more on that to come, but it's appropriate to mention at this point. So other things that are here is training, user training. That is part of the system, should be part of the plan. All right, so next one, systems engineering is an interdisciplinary comprehensive approach to solving complex system problems and satisfying stakeholder requirements. So again, here, the thread of interdisciplinary, comprehensive, so holistic approach, looking at the whole life cycle and all the components of the system. And then again, stakeholders. Stakeholders are not just the customer. It really is alluding to a larger pool of people that care about what you are doing or may be affected by what you're doing. If the environment is affected, for example, people care about that. Okay, another one here. Systems engineering is the selective application of scientific and engineering efforts to transform an operational need into a description of the system configurations which best satisfies the operational need according to the measures of effectiveness, integrate related technical parameters to ensure compatibility of all physical, functional, and technical program interfaces in a manner which optimizes the total system definition and design, and integrate the efforts of all engineering disciplines into the total engineering efforts. This one is pretty good too. It says a lot. First, we see the word selective mentioned. So you may think that all this stuff about the discipline and doing a lot of due diligence and thought before you actually do something is kind of philosophical and impractical, but it's actually quite pragmatic. And it has direct implications and direct benefits that are tangible and that are economic in nature. So the selective, we're going to apply selectively what we need to apply. It's not an exercise in over-engineering or overthinking or over-planning. Is what is the right amount of rigor that you need to apply to a given system, given its complexity? The answer to that question is also non-trivial. It requires a lot of experience and thought. The default is to actually to oversimplify things and to do less and be minimalistic about things that we need to do. It's human nature. It's just nature that systems and humans involved, included in that, we want to be in a lower state of energy. And if you take thermodynamics, you learn that that's the nature of systems, people included. So we want to be in a lower state of energy. If we are standing up, we'd rather sit. If we are sitting, we'd rather kind of slide down and kind of get more comfortable. So the tendency is to do less. So it's not that, and to prevent that, we want to keep in front of us and know and be very cognizant of the benefits of these disciplines. It's not unpractical. It's very pragmatic, in fact. So we're also mentioning here measures of effectiveness. You cannot improve, you cannot attain goals that you cannot measure, okay? And that you don't plan for. So a goal without a plan is a wish. And it may be great, but if you don't have a plan, and as part of that plan, tangible and measurable ways of see if you are attaining the right steps toward that goal, and demanding accountability from who's involved, then it really is hard to get there. It's really hard to get there. So it is important to have measures of effectiveness. How do we know that the system is going to meet the validation requirements and really meet the customer's expectations? Again, all that goes back to having good requirements. This also mentions interfaces. So important. Interfaces not only of the system with its surroundings. There are no system really exists completely closed from its environment, but there are degrees of openness. And some systems you can say that they're closed, but most are open and they interact with the environment. The understanding of those interfaces, as well as the interfaces within the system to make the system a reality, are important and a big part of the specification, the requirements gathering and management, and of systems engineering. And again, he mentions optimization for the total system definition and design. So again, a holistic approach, and the integration of all engineering disciplines, which again is the interdisciplinary nature. So you can see the threads, right? So another one here, system engineering is an interdisciplinary approach and means to enable the realization of successful systems. It focuses on defining customer needs and required functionality early in the development cycle, documenting requirements, and then proceeding with design synthesis and system validation while considering the complete problem. Again, operations, cost, and schedule, performance, training and support, tests, manufacturing, and disposal. Systems engineering considers both the business and the technical needs of all customers with the goal of providing a quality product that meets the user needs. So in this one, we see the recurrence of interdisciplinary approach, the realization of successful systems. So it is an approach that is going to enable us to have a successful system. A successful system is one that, to keep it simple, think in terms of these three pillars. It meets the requirements from a customer and user perspective. So it does what it needs to do. It can be developed in a timely manner, and it can be developed with a reasonable budget. So those three dimensions, features, functionality, how much it costs, and how long does it take to do, those are the primary dimensions of systems engineering and system level thinking and design. And if you focus on all three, you can get a very balanced and successful system, and it requires a lot of discipline. It's easy to actually, in a very, with a lot of lack of discipline, to just take two of those and not be very rigorous and come up with something. So you can spend a lot of money and take a long time, and I'm sure that you can come up with something pretty cool. But it took you a long time and you spend a lot of money. You can spend very little money and do it quickly, and then it's not so good. Or you could spend a long time, do something really nice, but it's going to cost a lot of money. So you can see that you can get two of those, but at the expense of the third. So the idea of systems engineering is, how do we get all three? And again, it's not trivial, and that's why there needs to be a set of systems or a set of methodologies and disciplines to achieve that. The other thing that is being mentioned in this definition is quality. So that's the other thing. Quality throughout the life cycle, not just at a specific part of it. All right, so that's a bunch of definitions of what systems engineering is, but it's a good compendium of them, and hopefully you can see by looking at different descriptions from different standards, different bodies, different people, but you can see that what is the recurring themes in what systems engineering is, and it's a great way to get things done, frankly. Now, if we drill down one level from a methodology perspective, and we're talking about complex systems, and we want to tame cost and also be able to execute in a reasonable time frame, the one thing that keeps coming back is simulation, and how it is used in the different steps of system synthesis, system validation, system verification. So we can start with simulations and different descriptions of the different parts of systems engineering and the description of the application that deals with problem definition, and you will recognize this list specifically as part of the deliverables of your project. It's coming, I mean, this list has influenced what I'm requiring there. So problem definition, formulation of objectives. So you have to understand the problem and then say, this is the problem, and to solve this problem, I have to have these objectives ultimately to solve that problem. Situation analysis, which is looking at the context of the problem and also what is available, things that are available, what have been the previous responses perhaps to this problem, that what have people done right or wrong. You can learn from both of those camps. That's important. And then think about what are the options, what are the different approaches beyond what people have done, how can you improve beyond that, and what type of tests or experiments you have to design to get more clarity, to get a clearer vision. So you're trying to get a clearer vision, and what is pervasive through all these points is trying to translate and elicit a clear need articulation from the customer to translate that into a good set of technical specifications and requirements that someone can design to and execute to that as well. So modeling is helpful in these endeavors. And then as part of your modeling effort, we're looking at data collection. You can synthesize data, and perhaps you guys are seeing why, there are some people that are saying that data is kind of like the new currency, because it's hard to design complex systems without real data. You can synthesize data, but it's not real. There is so much that you can do with that. So data gathering and designing the methodology and the process to get that data is important, so you can use it in your model design and use it to verify that you have a good model to work with. And ultimately, validation of the model results. So modeling is a central part of the early usage and engagement of the systems engineering way of thinking. And then you can run simulations. The nice thing about running simulations is that you can easily vary your parameters. You can vary your parameters and you can optimize your parameters. And you can store your results, share your results. That helps with the output interpretation. And ultimately, if you have good data gathering based on the problem that you're trying to solve, and you have a good model, you can come very, very close to coming up with a good design based on the model. It's never going to be the same as something, the real thing, but you can come up very, very close. And later on in the chapter, we're going to see that if we rely on this, we can actually accelerate the execution of the bringing into being of systems, because we are, by using modeling early on what we can do is maximize the likelihood of success or minimize the likelihood of a problem being found downstream when the cost is being multiplied through each stage of the hierarchy of the system, as I mentioned 10 times each time you go down the hierarchy and the phases of development. So it's a risk minimization exercise, and everybody likes to minimize risk. So modeling is very important in the context of systems engineering, and a lot of complex systems these days are starting to do what is called model-based systems engineering. So it's not just a bunch of disciplines and checklists and do this one thing after the other one. No, also have models built that can tell you whether the system is going to meet the requirements. So you are actually modeling not only the system, but you can model the faithfulness of your system requirements in relation to the needs of the customer. Now, one specific type of modeling approach is you can do time-based approach, different frames of reference when it comes to your modeling. One that should be highlighted that lends itself to complex systems and to cyber physical systems as part of that is event-based modeling. So another way of saying that is a state-based modeling. And the unit of gathering data or sensing and actuating and developing control, in the middle of that, the unit is based on the occurrence of events, not a linear timeline. So that works really well for complex systems like cyber physical systems, because you have a heterogeneous type of system where time means a linear time that we measure in seconds or milliseconds or days have different meaning for different parts of the system. So it may be that part of the system, a second is too fast, because perhaps the event density is in hours or days. But maybe part of that same system has a component that a second is forever. So how do you unify a common timeline without wasting a lot of resources and time when you have all these different parameters? So instead of looking at time as a linear measure, you focus on events without sacrificing the fidelity of the model. So event-based simulation for complex system is the way to go. So as I wind down this preliminary introduction to systems engineering, we want to emphasize the main activities of systems engineering: requirements gathering, looking at how the system is going to behave after its deployment, so things like reliability, looking at the onset when this system definition is being put together, what are the types of design disciplines that we're going to need to effectively bring the system into being. The evaluation of the different options for system design to solve the problem. Things like maintainability. How do we maintain it? Once it's in the field, what things do we have to put as part of the system design now so we can make it easier to maintain later and less costly? That is part of the system effectiveness. And of course, what are the tests that we need to do, not only for verification of the design, but also for validation of the design, per the distinction that I made already. So if we look closer to how we get to the business of defining requirements and managing those, and if we recognize how fundamental and how important it is to success, we see that elicitation, that having tools, coming up with instruments to have an effective elicitation of what the customer wants or think she wants and what is really needed. So and that's why formulation of the problem is important, because it may be fuzzy, it may be an ill-defined problem, but it is your job at the onset, if you're going to design a system, to answer, to have the solution to a problem, is you have to have it. And part of that is sifting through what are the real needs of the system and going a step further and also prioritizing those needs, because not all needs are equally important. Some may be more open for negotiation and trade-off and compromise than others. So there are tools for doing that as part of the systems engineering discipline, such as the modified house of quality that allows us to come up with a list and a ranking and assign a specific numerical values. So you have a guidance on what are the things that you can compromise on, what are the things that are really must-haves. And also, this specific tool gives you a measure of how difficult, the level of difficulty of meeting all these different needs. So that's part of elicitation, the analysis and definition of the requirements, and then eventually the validation of those. You do have to go back once you have that systems requirement document and go back and say, if we do this, what this document says, is the customer and eventually the end user going to be satisfied, and is the problem going to be solved from the perspective of those customers and users. And going beyond that, since nothing is written in stone, how do you manage the requirements in terms of making sure that they're followed? It's not just a nice document to just shelve it somewhere. So that's why you shouldn't, when you think about requirements, you shouldn't think of a lot of big documents with a lot of narrative. Very succinct, bulletized requirements. This is what we're talking about. We want to be efficient too. And as we'll see later in the chapter, that gets into what was first formulated in the Agile Manifesto in terms of software development. So, succinct requirements, but completeness, the efficiency of being able to articulate those is the key. So that you can enforce them from a design execution perspective, and also how do you manage change? Because there's always an opportunity for change, but if you have a good process to manage that, you can minimize the chaos that can bring. And actually, then the change may become an opportunity. It may become a competitive advantage for your team if you can react to that, to those changes gracefully from an execution perspective. So the business of systems engineering is actually a standard. It actually became a standard, an ISO standard in 2002, as a standard mechanism to create systems and products. So there is something established, and there is a committee that is part of ISO, the International Standard Organization, that curates the standard and adds to it and watchfully makes sure that it is relevant as time goes by. So we have a standard for the whole systems engineering process in 4 categories. Technical categories, and that's the one that we are most interested in. Project-related categories, so a big part of bringing a system into being is the program or the project management part of it that deals with resources, budget, timelines. But just the technical part is enough, so I always try to focus on the technical part. There is a whole type of discipline or job of people that are really looking at very methodically about the financial part, the scheduling and the resources, but there is not a clear line. Every type of technical decision has a financial, a schedule, and a resource implication, and vice versa. Every financial, schedule, and resource decision has an implication on what can be accomplished in a successful way from a technical perspective. So there is not a wall there, but systems engineers are more on the technical side, while maybe program managers and project managers are more on the business side. Then there is a section for agreement-related category. So again, that gets more into the business and then legal aspects, and the enterprise-related category, which is the overall enterprise company, etc. So what we're going to be, and what I have been talking about here, is mostly on the technical side with a little bit of the project-related categories, but mostly on the technical side, which is the hard part, by the way. So in each of these categories, the ISO standard comes up with these definitions of entities that are related to each other in the category. So activities, and there is a definition of what that is. And for example, activities essential to fulfill the design spec. So I want to wrap up now because I know I'm running out of time, but in the slides, there are the definitions. This I don't have to read to you. And these are the definitions of the processes in each of the categories. And also, there is a more comprehensive summary of systems engineering related entities in the table that follows that slide. And when you get the slides, you can read that on your own. And there is also another definition of systems engineering by INCOSE, which is the equivalent of IEEE for systems engineering. It's very nice that they made a different professional organization, because we don't want to think that systems engineering is electrical, computer related. It's actually much more. And so it's nice that INCOSE is there. And that's the definition from them, and also definitions for some of the other entities as it relates to systems engineering and the different categories that the ISO standard defines. So you can, again, read the slides on that, or when you get the video, you can just stop it and go through that and read the slides. But here's where we finish the introduction to systems engineering that I wanted to get done today. And then we can start talking about the design challenges inside a physical system representation as it relates to systems engineering. We can start doing that tomorrow. Thanks. Okay? All right.